Hey everybody. All right, this is the third and final episode of the outer astronomy videos that I'm making for my earth science class. Um, in this one, we're taking our knowledge of stars and we're kind of applying it to galaxies. And you'd be surprised at the things you can figure out just by looking at these pretty pictures. So look at the pictures we have right here. All right. As we start our galactic astronomy and cosmology talk, we can look at these pictures and start seeing entirely new things about them. Now, first of all, these two galaxies, do they look like they're connected somehow? Well, yeah, it looks like their arms sort of are almost reaching towards each other. They appear to have had a collision recently. And this is the case with many galaxies. So many of the galactic forms we see are due to collisions with other galaxies, sometimes very little ones, sometimes very big ones. But let's further look at this picture. When we look right around here, you can see a great deal of blue stars. All right, right over here, also a lot of blue stars. And up in this galaxy, more regions of blue stars. All right, so what's the deal on blue stars? If you remember last time we were talking, blue stars are the hot, really bright stars. And what's another characteristic? Yeah, they don't live long. They live 10 million to 100 million years, really nothing more than that. And in terms of the life of a galaxy, that's a very small amount of time. Whenever a lot of stars are born, a few of them are blue stars. Not a lot. But it doesn't take a lot because the blue stars make such a fuss. They shine so brightly that they outshine all the other stars and they color the part of the galaxy they formed in bluish. So wherever you see a lot of blue stars, you very simply realize stars are being born there. All right? That's a pretty neat understanding. Any place you see specifically yellow, like in the center of the galaxy here and in the center of the galaxy here, and maybe even along the arm here, there's a lot of yellowish. Yellow, well, yellow indicates there's no new star birth, that in the last billion years, 100 million years, no new action is happening that's forming stars. And when you look into those areas, for some reason, no new stars are being born. And it's in this study that we start getting to think of the reason things might be happening. Pretty cool. Just beautiful pictures, but you can think a lot more about them. So if we just start our talk about what a galaxy is a massive group of stars all bound together by gravity. It's an enormous object, and gravity has all pulled it together. Gravity works on the entire object, even though the object is vast. That's a kind of special thing about gravity. It works over these incredible distances, so it molds huge amounts of matter together in clumps. And inside that huge clump, a lot of little clumps form and form stars and all that stuff. But the galaxy is the sort of a bigger clump, if you will. So our galaxy has, they estimate somewhere between 200 billion or more than 500 billion stars. You can tell we have a lot more looking to do. But the smallest galaxy usually has 100 billion stars or maybe a little less than that, but it's an enormous number of stars, even in a small galaxy. And the largest galaxy have just trillions and trillions of stars. So our personal galaxy, from right outside your door, if you have a dark sky, a really dark sky, on a summer night and winter night, somewhere in the middle of the night, you can see, depends on the time of the year, you can look up and you can see part of this thing, I'll show you the picture, stretching across our sky. And That's our galaxy, the Milky Way Galaxy. So this is our galaxy, the Milky Way Galaxy. Look at that. Look at that. So that's the band of light that stretches across the sky. You're looking sideways through our galaxy because, of course, we're in the middle of our galaxy. So until we got really good methods of looking and methods of understanding, which were as important, we didn't really know what we were looking at. And now we've kind of figured it out. But some important points to maybe think about. Look at this right in here. See this dark lane running all through here, and you see it a little bit more in here. And what is that dark lane? Is that a place where there's no stars shining? Nope. It doesn't make sense. There's stars shining all through our galaxy. That, in fact, is a place of gas and dust where starlight cannot penetrate. And that's the very nature of the disk of our galaxy, to have a lot of gas and dust in it. Now, why is gas and dust important? You and I are made. All of this stuff is made of gas and dust. So gas and dust is what makes stars. So if you have a place of gas and dust, you are making stars. If you have a lot of stars, of those stars you just made, a fair percentage of them are going to, in their death throes, and even during their life, are going to emit enormous quantities of gas and dust. So the cycle repeats itself all through the galaxy. So we live in an active galaxy, a very active galaxy. You can see, just looking through it, that it sure seems like some of the stars we have in that plane of the galaxy are bright blue stars. And that means star formation is ongoing, that it's happening in our galaxy. So that's the Milky Way. Now, of course, this is just an artist's image, but this is a wonderful image. This is what we believe now, what the Milky Way Galaxy actually looks like from outside. So we are, we think, in a barred spiral. And we've gone a long way past the we thinking part, because we have such good orbiting satellites that are so remarkably efficient at figuring out not just all data from a star, but the star's location as well. So we've plotted stars, and we've seen the structure in our own galaxy, even though we're seeing it sideways. It's much like a kidney cell inside you suddenly using some advanced technology and figuring out what you look like. It's actually probably easier for us because we can see through space. Kidney cells, I think, would have more of a tough time. But take a look at what we have here. We have in the center, we have this barred spiral. Now, again, we were talking about the color of stars. What color are the stars there? I hope you said yellow. That's right. What color stars are missing from there? Yeah, blue. There are no blue stars there. And what does that mean? Just with our naked eye, we can look at this galaxy and start figuring out right away what that means. There's no blue stars there. So is star formation ongoing? No, because star formation isn't a slow process. If star formation were happening, it would be going on for like the last billion years, or a good while anyway, and it would have some bright blue stars still alive there. Certainly when those yellow stars formed, some blue stars formed as well, of course. Well, what has happened to those blue stars? The answer is they have died out. So there's no blue stars left, just a yellow star population. So you can be quite sure no new star formation is ongoing there. Now, at the same time, take a look at the arms extending away from this. This is the Centaurus Arm. Okay, look at that beautiful arm. And then there's another arm here, Sagittarius Arm, which turns into the Perseus Arm. Of course, these are some of the constellations found clearly sitting in the arm. But here we have a sub-arm clearly a sub-arm, not to disappoint you or anything, but you live on not a main arm, but rather a sub-arm of the galaxy. It's a cool place, though. It's like sort of a special location, the Orion Spur. Pretty cool location right here. Do you see it? The sun. So we live right on, it's a nice little cul-de-sac location. If it ever goes up for like sale, it's gonna fetch a lot because it's a lovely, and it's got water in view. So this is what we think our galaxy looks like. You can see some arms attached to this central bulge. You can see that those arms have some other substructure to them. We're not the only sub-spur going on, but there's some complexity here. This is a spiral galaxy. These spirals, well, let's take a look at them with our newfound knowledge. And what can we say about these spirals? All right. Well, if we look closely, these spirals seem to suggest that, well, they're blue, aren't they? So it means that stars are forming along them. For some reason that's not happening in the center of the galaxy, along these spiral arms, there's blue. Look a little closer. What other color do you see? I'm on a little closer, it won't bite. Actually, it's a galaxy. It could do anything. But from this distance, you're okay. It also looks like there's red stuff, there's pink stuff. Now, if you were to look closely at that, those are nebula. Those are places where, when I was showing you back in the stars video, those are places where stars are being formed. So those are enormous star birth locations. They're also locations, of course, of star death. Those things go hand in hand, and because every time a star dies, it leaves a lot of heavier elements to the universe or to its galaxy. The next stars that form incorporate those heavy elements. Notice, I am not sitting in hydrogen here. There's a lot of heavier elements here. I myself am not just made up of hydrogen, even though that's my most common gas. So in this galaxy, all the things going on really relate to the here and now of our very own existence. But that's what we think our Milky Way galaxy is, and have some appreciation of the astronomers who are able to piece together through evidence. And that's a pretty good description of what our galaxy, what the model is currently, and they've come a long way. So when we look out at our Milky Way, if you were to hold up a finger and to cover up some of the Milky Way, some of the haze you see there, you're actually probably covering up 1 billion to 10 billion stars in the distance just with a finger. There's so many stars. You can't see the individual stars, but it's sort of like a cloud of dust where you can see the cloud is there, but you can't see the individual chunks of stuff that you know make up the cloud itself. When I first recorded this years ago, there were 50 billion galaxies visible, and that was a number too large to comprehend. It's more than 1,000 billion, which is a trillion, more than 1 trillion galaxies, not stars, galaxies, more than 1 trillion of them in our observable universe. Lately, the number seems to be pushing 2 trillion. But as we start being able to observe more and more, it probably won't go down. So in our own galaxy, our solar system is located about 28,000 light years from the center of our galaxy. Not quite 30,000 light years, 28,000 light years from the center of our own galaxy. And the center is a very active place and an interesting place. So if we wanted to look further back in space and time, how would we do that? If we were to take a very long exposure, a film exposure, a photographic exposure of the emptiest spot in the sky that we can find, what would we see there? That was a question that was posed to the Hubble team early in the Hubble Space Telescope history. And although a lot of astronomers resisted taking large amounts of Hubble Space Telescope, the most valuable telescope on the planet, a lot of astronomers were very upset with that idea. But they then decided, well, the Space Telescope Science Institute anyway, decided to do it. And they took 10 days of looking in one spot. All right? And we're looking for galaxies so far away, it takes billions of years for that light to get to us. So we're seeing those galaxies as they looked billions of years ago. And the deeper we look, the more galaxies we find. This was a really cool image taken by the best telescope we've ever had so far. And if we take a look here, just take a look for scale, these are some astronauts that are working on the telescope. The Hubble telescope, one of the things that was so good about it, we know our technology has increased incredibly in the last 20 years, 25 years or so since we've put the Hubble telescope up. Actually, it's more than 25 years. So we now have, even though it's the same mirror on the telescope, we now have the ability to see so much better with better cameras. So we continuously have installed better cameras over the life of the telescope. And the astronauts have worked to upgrade the telescope in the most incredible ways. The astronauts, one of the big, amazing things the astronauts have done in the last few decades, along with building the International Space Station, has been maintaining the Hubble Space Telescope. And that has been a wondrous undertaking. And they have changed out the camera numerous times, and I'll be showing you images from those different cameras. One of the best things they did, though, was put an unprecedented detector in there that would detect infrared. If you look at your electric spectrum, after visible light, where the wavelengths are getting longer, it's infrared, and it's a big section of light, and it's from atoms that simply aren't quite vibrating enough for you to see them, but they're vibrating a lot, and you know that means something. I could stick a poker when I'm doing blacksmithy stuff in the fire and pull it out before it starts glowing. Do you want to touch that? No, that matter is busy matter. So if in the sky it's giving off that kind of heat and those wavelengths, we want to see it. They put a detector on this where they had to run plumbing outside of this and do some amazing things to make this work. But they did a great job. And that near-infrared camera was simply amazing. And we have been seeing deeper because of it. So this is the very first deep field with the first generation camera, where they took 10 days and they set it looking at nothing in the sky. There is one star. Okay, can you see the star? That's right here. You can see the spikes on it. Spikes from things like that are the internal optics of the telescope. Have nothing to do with stars giving off spiky things. But look at that. Everything else is a galaxy. And pretty much they were not visible from Earth before. And I want to circle an example of a very special one. That reddish galaxy. We're looking so far across the universe. We're in the middle of a big bang, so everything is going fast and moving away from us. The farther you look back in space, the faster everything is moving away from us. Inside that circle, you see a little red dot. That little red dot is moving away from us. It's just a regular galaxy. It's white like a regular galaxy. But it's moving away from us so fast that the light has been stretched out. And what's the longer wavelength going to be? red. So we're just seeing the red of it. If we could look at it with infrared, and of course the Hubble now can, if we looked at it with infrared, we'd see it even better. And if we could look really deeply with infrared, we would probably see a truly amazing sight. But these are the galaxies we could see. Some of them, the littlest dots, seem over 6 or 7 billion light years away. That's staggering. Well, why stop being staggered? Um, with the third generation camera, with the second generation camera they did too, but here's the third. This is with a much better camera doing the same sort of thing. Every dot in this picture. Oh, wait, no, maybe this is a star. I think it is. It's one dim star in our galaxy. If you look hard, you might be able to find some more. That's the first one I've found. But every other dot is a galaxy. And as they get further away, they seem to change. Remember, we're actually looking backward in time. We're looking billions of years into the past. What we're seeing is the evolution of galaxies. These galaxies all play together, and they change form as they interact. So while stars are a great distance apart, galaxies are close enough that they regularly are interacting, often colliding and tearing each other apart, adding to each other to create new forms, all sorts of interesting things. Pretty much anything you could imagine galaxies are doing here. But stars are so far apart that two galaxies can go through each other, and there's a really good chance that no stars will actually collide. So we did not understand when we first looked out why we see so many different forms of galaxies. And now we think it's because of galaxy play. As they interact, these forms tear each other apart, they stretch, they change as they get slammed by other galaxies. Those density waves may go out that might make a spiral galaxy be a spiral galaxy and have all its wonderful star formation. So one kind of galaxy becomes another kind in this dance of galaxies. Our nearest neighbor galaxy, I'll show you a picture of. Um, these are the different types of galaxies. So you see the barred spiral, that's what we believe we are. In the middle there is the irregular galaxy. And what do you notice about both the barred spiral and irregular? And in fact, the top right side, the spiral galaxy there, if you look, there's blue. And what does blue mean? Blue means, of course, star formation. So if stars are being formed, that says something about the galaxy. Peculiar, on the lower left, does that look like star formation? It does to me. And very often peculiar will have great amounts of star formation. If you look at the last two, however, elliptical and lenticular, they look distinctly more yellow than anything else. And indeed, elliptical galaxies don't really show much texture at all. These two, or this elliptical galaxy is unusual in that you could see some dust clouds in there. But even with those dust clouds, doesn't look like there's any star formation. So when you see the red, it's indicating star birth. When you see the blue, it all indicates that the galaxies are quite active. And those are the major types. So here's the spiral. You distinctly see the inner part with yellow, the outer with blue. This is our nearest neighbor, the Andromeda spiral galaxy. We see it sort of edge on. Now, interestingly enough, this galaxy is on a collision course with our galaxy. Our sun will probably live plenty long enough to see the collision between it and this galaxy. And we will collide and do all these unusual forms, some of which you'll see it on some of these slides, where we do this gravitational dance, and we'll end up swirling around each other. And we'll end up, we could think that we're consuming each other, but we're playing. These two galaxies will play. Our sun will, like most of the suns, like almost virtually all of the suns here, will have no problem with it. They won't. They will maybe go by other suns. It might ignite formation of a lot of comets in skies as the comets come in from somewhat nearby passing stars. But the odds of two stars interacting in any negative way, the distances between them are so vast that it's unlikely. If you look in the summer sky, if you look at the Great Square of Pegasus, find a star map. It's easy on your phone or somewhere. If you look at the Great Square of Pegasus, off one of the arms of it, one of the bottom stars of it, is a constellation called the Andromeda Constellation. And if you look, there's some stars that point very easily towards this. So with a pair of binoculars, it's easy to find this. One of the funnest times I've had is showing people this with binoculars, because it's a fuzzy spot in the sky, and you can tell somebody to look at it with binoculars once you know where it is. It's the farthest your naked eye can ever see, and with binoculars, it looks a lot like this, and it's remarkable to see in the sky. It's actually bigger than the full moon. So the Andromeda Spiral Galaxy, I would recommend it. This is one of my favorites. Historically, this was just incredibly cool. One of the first shots that the Hubble Telescope took when we fixed it, and it got all better because when it was sent up, it was they had made the mirror ever so slightly the wrong shape. They had sort of done the math ever so slightly wrong, and nobody caught it. Even NASA makes mistakes. But then they figured out how to fix it. And the first image they sent down was this, and we were able to compare it to an earlier one that was rather fuzzy, and then we saw this, and we could all realize immediately that this was going to be the funnest telescope ever, and we've been getting the most incredible images ever since. So M100 is just a stunningly beautiful galaxy, and you can look deep and deep and deep within it. And well, what do we see right away that we now understand about galaxies all along the outside of it? Do we see blue stars? Yes, we do. Does that mean star formation? Yes, it does. Does that mean a lot of gas and dust? Well, yes, it does. All right. Now, if we look deep in the center of it, do we see star formation? Apparently not. Now, why all this? That's a separate issue. But that you could just now see that with your eyes when you see those dark lanes, right? Let me point out the dark lanes right here. Notice these dark lanes. What does that mean? Is that a place with no stars? No, that's a place filled with gas and dust. So much junk you can't see the starlight through it. So that's what those these big arms are. These dark places, they're all places where there's so much gas and dust you just can't see through it. So there's a barred spiral. Again, you can see places where stars are being born, places where stars are not. So you can right away start seeing into galaxies and then understanding why they work. It's not so hard. So when I was a kid, that image in the center, this whole image, that's what I had to look at in any star books or anything that was published, or the best pictures astronomers had. We were able to see galaxies like that, and that was an incredible image. But we could do so much better with our current generation telescopes. And just to compare, in the center of what I've outlined here, you can see a little blue box. And then look at the upper left where it says WIFPIC 2. That blue box is what we look at with our Hubble telescope with the wide field planetary camera number 2. That's in the middle of the 1 and 3 that I was showing you before. So that wide field planetary camera gave us some incredible images, and this is one of them. We looked right in the heart of this galaxy, in this barred spiral, a really interesting barred spiral, and we saw that incredible image from deep in there. If we look deeper in that blue image, we see a red box, And over on our lower right, we see an image called the NICMOS, and that is the near infrared camera. And I don't remember what MOS is, but that's the near infrared camera that astronauts installed on the Hubble Space Telescope, so we could see incredible things like that. Because when matter is pretty hot, you want to see what it's up to. So we're able to see that much better than we could see from the very best pictures we had when I was a kid. And that center image, that's the very best picture by far that the entire human race had of that image. Look at that. That's a beautiful picture. And as you look at these, you can see what they're made of. You can see how they're working a little bit. You can see their individual arms. You also see that they're made of hundreds of billions of stars. And I can show you picture after picture after picture, picture after picture after picture of galaxies. And they're made of hundreds of billions of stars. It has to make you stop and go, whoa. That we now know that most of these galaxies, most of them, that most of these galaxies are filled with hundreds of billions of stars at very least, and that most of these stars have planets around them. That's a very, very common feature of star formation, is forming a group of planets around you. When you stop and think of that and what you are looking at, even a centimeter of that image of the tail going out, you're covering up tens of billions of stars. So when you look at that, it has to impress you. But if you really want to be impressed, this image, when this image came down, this is called the mice. This was from the near infrared camera number 2. And or I'm sorry, not the near infrared, that's wide field planetary camera number 2. They had installed that on the Hubble Space Telescope in another servicing mission. And while the first one wasn't broken, we knew this one would be so much better. But how much better? We didn't know until we took this picture. In this picture, most of the objects, not all, but almost all the objects were not anticipated to be there. Those are all distant galaxies. This was able to take such an amazing picture. If you look at those images closely, you'll see each and every one, except for the one with the spiky things. Those are the couple stars in there. But each and everything you're looking at is a distant galaxy. We didn't think we had made a camera that good, but we did. That camera was just amazing. So another kind of galaxy are elliptical galaxies. Take a look at that. What do you see, or perhaps what don't you see? I don't see it either. I don't see any blue stars. In this galaxy, there have been pressures from enough stars that it's blown all the gas and dust pretty much out of the galaxy. Now, no worries. It went to interstellar space or intergalactic space, where sooner or later it will probably recondense and fall on some other galaxies and do star formation again and more galaxy play. But this galaxy is just shining yellowish and reddish stars. That's all that's left. So no new star formation. It doesn't mean there aren't civilizations and wonderful places and beaches and all that, but there's no new star formation. All right, for regular galaxies, these are usually small galaxies that have not really got their act together yet, but no worries, because a lot of them are about to be swallowed up by much larger galaxies. That's the case for this, our nearby irregular galaxy. But what do you see there? Yeah, star formation. Lots and lots of star formation in all sorts of regions. So there's density waves pushing through them. They're having a lot of fun. Well, what would make a galaxy then peculiar? Usually because another galaxy punched it right in the eye. Yeah, that would be something like that. And so after a collision, pretty much any galaxy is going to look a little peculiar. And so they go from one form to another. So we, at some point, will probably be able to be described after the Milky Way or after the Andromeda punches through the Milky Way, we'll probably be able to be described as peculiar. And we will be. But then we will slam the Andromeda Galaxy over and over again, and we'll be very peculiar, and eventually we'll settle as elliptical. So galaxies go through these forms. One is the way it is because that's where it is in its life. We're pretty sure of that. Okay, guess what two galaxies look like they combined here? I'll give you one guess. Okay, an elliptical and a spiral. And that's what it looks like, and probably has something to do with what its form is. See, now it gets a little scary. When you go beyond, galaxies are mind-bending. They just like, oh my word, there's hundreds of billions of stars in a galaxy. Are you kidding me? Right? Hundreds of billions with like trillions of planets in a galaxy, and we're talking there looks like there's 1 trillion or 2 trillion galaxies that we could see. All right, so like let's just go crazy. Beyond galaxies, when you start looking, it seems like there's more to see. They come in large clusters, all gravitationally bound together. It looks like there's an even larger structure in the universe. Not just galaxy clusters, but what galaxy clusters are part of. So there's places where it doesn't seem like there's much matter at all. And there's places where there's a lot of matter. Here, a lot of matter here. Whew. Here you have a group of closely joined galaxies. This got its fame in the start of It's a Wonderful Life, the Jimmy Stewart movie. Frank Capra directed a wonderful holiday movie. You might want to watch if you haven't seen it. It's a Wonderful Life. I still cry all the way through it. But at the start, they had to find something to look sort of like God. And so they picked a picture of these galaxies. And they lit up and talked to each other. But that's the actual galaxies. And even in an old space telescope picture, or not a space telescope, even in an old Earth-based telescope, these looked pretty cool. So they look really cool in a Hubble telescope. It's more galaxies gravitationally bound together. Galaxies play. Notice on the right side of that is a galaxy that looks just like an eye. We know the others look like spiral galaxies. What's that one? All yellow, doesn't look like new stars. That's an elliptical galaxy. Yes. And those sawtooth marks in the picture, that was from WIFPIC 1, the Wide Field Planetary Camera 1. Just the way it was made, the way the electronics were set up, that's what they had as an artifact. So you know when you see that sawtooth in the upper right, like that, you know you're looking at a WIFPIC 1. No worries, they were awesome pictures. So in the last few decades, our observations have gotten so good, and we've used that combined with our computing technology. It's improved to the point where we can put together the structure of the most distant galaxies. When we do that, what we find, we call, and you'll see why, is called the cosmic web. So we have huge filaments of galaxy clusters strung together, surrounding vast voids where there's few, if any, galaxies at all. And it looks remarkably to be a structure. And every dot you see in this structure is not a galaxy. It's a galaxy cluster, a cluster of hundreds or thousands of galaxies. It's not a science fiction image. That's what we think is there. It's a computer representation, of course, but it shows you places of great densities and places of these voids where there is not even galaxies. So it looks like there is some structure to the universe, which makes this a very fascinating study. Why is there structure? What does that mean? And to recognize that we, from this planet, our technology is advanced to where we can see that, that is absolutely stunning. So let's talk about how we know what we know. Most of what we know from the universe we've learned from analyzing the light that reaches us from distant stars and galaxies. Light is in the form of electromagnetic radiation, which is energy that travels in waves. And look at your earth science reference tables, and you'll see the chart on electromagnetic radiation. It shows all the kinds. You have the gamma radiation, the X radiation, and the ultraviolet. Notice those are all words that sound a lot like warning, don't go there. Those are the more energetic radiations that, yes, they're bad for you. So try to get minimum doses of them, especially those pesky gamma rays. Then you have a tiny little line called visible light. Then you have a big chunk of infrared, which is hot, but not hot enough for your eye to see. And then after that, you go to microwave radiation, which is just the right wavelength. We can actually use it and vibrate atoms or molecules of fat and water in our foods. And because they just happen to resonate with those waves, we can cook things quicker. In microwaves. We use microwaves. Your phone uses microwaves to communicate. And then even longer waves are radio waves. So we have a variety of waves, and you know that those waves are much less dangerous in general to you, a lot better than X-rays and ultraviolet anyway. So if we take all those waves, all of them, and stretch them out and put them on detectors, we can find out all sorts of information. And that's what we do. We use spectroscopes to separate the starlight into its colors. It's a lot like using a prism to make a rainbow. So by analyzing and comparing these different spectra, astronomers can figure out what elements make up the atmospheres of stars and planets. They can also determine the speed of galaxies. So you realize right away there is so much information in that light. When you dissect that light, there is so much information. So when we look at composition, when we try to figure out what things are in it, we do this in a lab. And we can see these gases, and you can identify them by, you can make a bright line spectra by doing, putting electricity through like a neon bulb. A neon bulb is that, and just neon gas, when the electrons jump up, they all fall, and they all fall exact amounts, and that releases a certain extremely specific wavelength of light. But in the same way, if you have a star and say that neon gas was a cool gas between the star and us, that cool gas would absorb just those wavelengths of light, and its electrons would jump up and then jump down, but they would shoot the light in all directions, not at us necessarily. So that light, those little wavelengths of light, would be missing in the atmosphere. And sure enough, we could do these experiments on Earth. We could look at stars and we could see exactly what they're made of. As a matter of fact, if you want to see what something's made of, you'd heat it a lot and look at it like this, and you can see what it's made of. So stars and spectroscopes can show us what is going on there. So star heats the gas up. A spectroscope will show us all the elements. We just compare it to results in the lab. And yeah, we've done that. So we know what all the little lines mean. We've done a lot of work to make sure we haven't missed any little lines. Because if we were missing some little lines, there's some science there that somebody would want to do. So we've really worked on figuring out what elements are in all these different stars. In terms of speed, all those lines can be shifted either to the red or to the blue end of the spectra. We know the patterns of the lines. We've seen that a million times. So if we see that pattern shifted, it must have been shifted for some reason. And that reason is the Doppler effect. And that tells us all about the speed of these things. So spectral analysis tells scientists not only what the stars are made of, but how they're moving in relation to Earth. This is just basic Doppler effect. So we should talk about a Doppler effect. Have you ever heard a fire truck pass by? Forget a fire truck, a car. Have you ever heard a car pass by? I think we've all heard a car pass by. Can I do the sound of a car passing by? Here you go. Sit down. Wake the kids. Ready? There you go. Car passing by. All right. What was that special about passing by? I had a high frequency as it was coming towards me, and it stretched out to a low frequency as it passed. Notice it was not just volume increase. It was not just doesn't sound like a car passing. That's the volume increase and the volume decrease, but something else happens. High frequency, when it passes you, it goes to a low frequency. You've heard that your whole life. That is the Doppler effect. When a car is coming towards you, or when anything like that is coming towards you, and it's using sound waves, the sound waves are compressed as it pushes them closer together, as it's coming towards you in the same direction the sound is going through. So with that compression of the sound waves, you hear them one after another a little faster than they were actually emitted from the thing. We would call that a higher frequency. Then when it's pulling away from you, it's doing the same thing in reverse. It's stretching those sound waves out. So the sound waves are hitting you a little slower than they should from what it's actually being produced. And we'd call that a lower frequency. So high frequency to low frequency, just as volume goes at this highest point and then starts going down. That's the whole thing. That's it. That's the Doppler effect. So the sound of the siren, if you're just listening to a constant pitch siren, if it's going wow, 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 it probably gets confusing. But if it's just, right, if you think of that, pitch grew higher or stayed high as it approached you, and suddenly dropped as it goes past you. And it's from one high pitch to a low pitch. And this is a good example why. Take a look at that. From stationary, all around it stays the same length of wavelength. But from a moving object, in the front of its motion, it gets squished together. Behind it, it gets stretched out. So when something is moving, higher pitch in front, lower pitch in the back. For something moving low speeds of Earth, as long as they're going kind of fast enough like a car is going, like notice you don't really hear it with a bicycle. They're kind of going too slowly. You can hear it a little bit, but it's much more pronounced with a car. As you get closer to the speed of sound, of course, it becomes more pronounced. So it has to be something going decently fast. Cars are going plenty fast enough to do it. Notice, though, when you look at the light coming off of a car, the car doesn't ever look bluer. And as it passes you, it doesn't ever look redder. It's because light is moving so fast compared to the speed of a car that does happen. That really does happen. When you are busted by a radar detector from a police officer, they shot you with that radar detector. That is light, and they bounced that off. They received its frequency. By checking that frequency, they knew that you were actually changing the frequency because you were going this fast. That's how come you got a ticket. So speed of light busted you there. So it does change. But to our eye, it would never look bluer or look redder. You just don't go that fast. But when I showed you that picture of that galaxy, and I circled it, that galaxy was going fast enough to look red. The galaxy itself was not red, but it was going away from us so fast. Space was expanding between us so fast that it was able to stretch those wavelengths out. So we saw them as red. So you have to be going very fast if you're playing with the speed of light, but not all that fast to play with the speed of sound. So that spectroscope allows us to see all the information light contains, allows us to determine many things. The composition of stars and galaxies. The conformation confirms stellar evolution. I'll give you an example of that picture in the deep field. Well, a star belonging to a galaxy really, really far away. Is that star going to be made of many heavy elements? Think back on what stars do. Stars make heavy elements. So if it's a first generation star, it was made of just hydrogen and helium. That's all the universe was made of when it was created. So it wouldn't be full of all the metals, of the heavier elements. So it would give off a spectra that says hydrogen and helium, and not much at all of the heavier elements. When we look at the spectra of those really, really distant galaxies, guess what we find? Not many heavy elements at all. When we look at the spectra of much closer galaxies, we find, similar to us, much more heavy elements. When we look at the spectra of nearby stars in our own galaxy, much more heavy elements. So as we've progressed in time over the life of the galaxy, over the life of the universe, we get heavier and heavier galaxies, get heavier and heavier elements. So we've confirmed what the composition of stars and galaxies is. And because galaxies are made of stars, what those individual stars are doing is really important. So that gives us an overall spectra. But early galaxies are lacking the heavy elements. Galaxies later in the formation of the universe have a lot more of the heavy elements. No doubt, 20 or 30 billion years from now, a lot of galaxies will have many more heavy elements than we currently have. Our sun is shining. It's making heavier elements. All the stars you see shining in the sky, they're making heavier elements. So galaxies evolve and change, just like planets evolve and change, just like creatures evolve and change. Change seems to be the catchword of the day of the universe. So we also understand the speed of stars and galaxies. We find that all distant objects, really distant galaxies, they're all moving away from us. None, I repeat, none are moving close to us. Now the Andromeda Galaxy, yes, is on a collision course. Inside galaxy clusters, like we were saying, galaxies play. But as soon as you get a certain distance apart, no, like by 20 light years apart, no galaxies are really coming towards each other anymore. Space is expanding between them. And when you double the distance that you're looking, space is expanding twice as fast. 3 times the distance, space is expanding 3 times as fast. It's like raisins in French bread, or in like bread dough. Think of bread dough expanding with raisins in it. Each raisin has bread dough in between it, and that bread dough all expands at a certain rate. So if you're 3 raisins away, you would expect the bread to be expanding 3 times as fast because there's 3 times as much bread dough. You have more universe between you, the galaxies go apart faster. When we look at galaxies on the far edge of things, they're red because the universe is expanding. There's so much universe between us and them, it's all expanding tremendously fast. It would be completely incorrect to say that galaxy is traveling nearly the speed of light, even though we're expanding, in some cases, at nearly the speed of light. We're expanding that way because there's so much universe in it. Neither of our galaxies, we look the same to it, by the way, neither of our galaxies are actually going that fast. It's the universe expanding between us. It's a hard thing to wrap your head around. So we have the evolution of the universe. We have just what I'm talking about, how galaxies show us the evolution of the universe. But there's another story in there. There's the story of the cosmic background radiation. So the cosmic background radiation is one of the great science stories, and I'm not going to put too many details in here, but a team of scientists at Princeton University had predicted that if the Big Bang actually occurred, and they didn't know that it had occurred, they're just predicting if it did occur, all the theories, all the physics we understand suggests that we would still see the heat left over from that explosion. But the heat would be really stretched out, so it wouldn't be a really short wavelength anymore. It would be a much longer wavelength, but they were very precise on their wavelength. 2.7 centimeter wavelength. Okay. And where should it be coming from? Everywhere. Everywhere you look in the sky should be this 2.7 centimeter wavelength. Further down the road, in New Jersey, was Bell Laboratories. And there were 2 new PhD students, scientists, they'd just gotten their PhDs, who were given, basically, from Bell Labs, this huge radio telescope. And they were allowed to do science with it. So they're good scientists. What's the first thing you do if you've just been given an amazing science instrument that you could really do science with? Well, the first thing you do is calibrate it, is make sure you understand the instrument, that if the instrument is saying something, you know the instrument well enough to know that it's saying something real, not some internal weirdness of the instrument. So they turn it on, they start working it, and sure enough, what do they find? The instrument's weird. The instrument constantly, no matter what direction they point, no matter what season of the year, no matter what time of the day, the instrument always has this buzz associated with it. And it's a buzz only a telescope like this would ever pick up. But it's weird. It's just a signal. It's not anything you would really think of. But it shows that something's up, that they need to understand it to say they understand their instrument. And it's pervasive. They can't figure out what it is. They check every source they can think of. There's even stories that they had to get rid of some pigeons because they had roosted in the telescope, and then clean out all the pigeon droppings because they thought maybe that, on a long shot, maybe that was ruining their instrument. But sure enough, their instrument was still broken, and it kept giving this 2.7 centimeter radiation buzz from the entire sky. They couldn't figure out why. And then somebody told them, call this other laboratory. The director of the laboratory picked up the phone, didn't give them a lot of information, just, yeah, okay, we'll check it out. When they said they had this 2.7 centimeter buzz all over. And these people at Princeton had been working forever to figure out a way to build a telescope cheaply that would detect this 2.7 centimeter radiation and get them the Nobel Prize. And the guy put down the phone and said, fellas, we've been scooped. They knew they weren't getting the prize. They had predicted it, but they didn't find it. The fellas down the road, Arno and Penzias, had found it, and they got the prize for finding the cosmic background radiation. So we find much evidence. That's the best science story, because here some people predicted it. They didn't have a theory that says the radiation is some wavelength, some particular. No, they said 2.7 centimeters. They didn't find the radiation and then come up with a theory to try to explain it. Now, that doesn't mean the theory isn't good, but coming up with a theory that says this should be the exact size and it should be everywhere, and then a totally independent team finding it, come on, that's pretty good. And that was amazing. So gave us a lot of reason to suspect that we're right about the cosmic background radiation being leftover voice of the Big Bang itself. Give me a second here. Yeah, it's heavy stuff. You can hear the Big Bang. You can hear the Big Bang in this radiation. You can still have the explosion. Crazy. So all the material is still rushing apart. We live still in the middle of this explosion. When you look outside, the sky seems so tame, so calm, so not at all like there's going to be a collision. It's going to be 2 billion years or more before there's a collision. So I would say we got some time. You don't have to worry about it or pack things up. But the sky is a busy place, just not compared to a human lifetime usually. Usually it's pretty calm and sedate. And for your great-great-great-great-great-grandchildren, they will still see the constellations in exactly the same spots, even though the stars are really moving quite fast. But they don't change that fast, not compared to a human lifetime, or a lot of human lifetimes. We do know that the universe is huge and it's growing. There's debate on its future. What is all the long-term prospect of it? We think over the great expanse of time, the universe will continue moving apart. There's evidence now that the universe seems to be accelerating, which it's funny because that was never an option for the universe to be doing. The question was there enough gravity to stop it, or was it just merely going to be slowed down and still slowly drift apart? But no, in the last 20 years, we found evidence that it seems to be not just drifting apart, but accelerating. And we don't even know what force could do that, but it seems to be accelerating as it goes apart. So there's much more to learn. Here's a picture of the cosmic background radiation. You can see it's not uniform, and that's a really important feature, that if it was uniform, notice you and I are not that empty space. So the universe isn't uniform, and the cosmic background radiation suggests that structure will occur in the universe. And sure enough, you and I are structure in the universe. And those holes where there's no structure is places where there's no structure, or there's those great voids in the structure. But the cosmic background radiation, it almost suggests something like the cosmic web. You can see the two would be related. So here's just a thing on the redshift. Think of a star coming towards you. Think of a star moving away from you. And then if you look at the three diagrams, you have the unshifted thing here, right? That's the elements unshifted. Now look at them redshifted. Look at them redshifted there. All right, redshifted, they're all pushed into the red end of the spectrum. And now the last one, look at them blue shifted here. They're pushed into the same spectral elements, the same distance bar, just pushed into the blue end of the spectra. And that's all we're talking about with the Doppler effect. And that's when we look out at distant galaxies, we see none, zero that are blue shifted. All distant galaxies are red shifted. And if they're twice as distant, guess how much more they're red shifted? Twice as much more. All right, one more time. They're 3 times as distant. Guess how much more red shifted they are? I'll give you a second. 3 times more red shifted. That was excellent. Guess how many at 3 times that, or that huge distance? Guess how many are blue shifted? Go ahead, I'll give you a second. No, that's wrong. I'll give you another second. Correct. 0, none, nada. No galaxies at that distance are blue shifted. None. And if you go farther, guess how many are blue shifted? If you look all around, guess how many are blue shifted? There's no blue shifted. Everything is red shifted. So do we have evidence that the Big Bang occurred? If you run this movie in reverse, all the galaxies are coming together. All these galaxies coming back together would be the reverse Big Bang, kind of the big get-together. But the Big Bang does appear to be the best explanation for what we see in the sky. And we have ferocious evidence that this is what happened in the sky. It's not like ferocious evidence that says, yeah, the Earth is a sphere. But it is such an amazing amount of evidence that it's hard to come up with another idea of why everything is rushing apart like that. Or just to explain the Doppler effect that we see on everything. Is there some other explanation? Well, scientists have worked at other explanations. None makes any sense at all. And amusingly, this was actually predicted by some of Einstein's early theories. So, is this the end of astronomy? Well, it's the end of the astronomy unit. But the study of astronomy is the study of your origin and the fate of your world and the universe. It's a big story. There's still so much to learn. We have had science around for 400 years. Before that, we were naming the constellations and pretending that maybe it had something to do with reality. That maybe Orion was Orion, maybe... No. Now we know what's going on. And it's a much cooler story. It's a much cooler story. And we've barely scratched the surface. Realize that every other study is basically what's happening on our little speck of the planet. And astronomy is about the entire rest of the universe. It's something worth thinking about. It's something worth caring about. It's something worth looking up and speaking in hushed tones and knowing that you're in a really serious cathedral under the night sky. When you look at the Milky Way stretching across and you start seeing some of the detail in it with your own eye, start knowing some of the things that's going on, that's just cool. That's just cool. It doesn't need any other reason. That's just cool. In your mind, just in this lecture, you know so much more about things like galaxies. Galaxies vast beyond comprehension. You can look at them and know what's going on. So if you could do that in one little lecture, how much more can you do in a little bit more study every day on anything you're really fascinated by? But astronomy is well worth being fascinated by. Have as much as you'd like. It's all there for you. Peace out.